All right, so the lecture objectives in the segment are to use kinetic theory to explain the gas law, ideal gas law. Use kinetic theory to relate speed of effusion to diffusion to molecular identity. Okay, so kinetic molecular theory. This is a theory that works quite well and shows, you can prove why the ideal gas law works. You assume that the particles occupy approximately zero volume, which is pretty good. Gas is mostly empty space. You assume that collisions are elastic. When molecules collide into anything, there's no loss of kinetic energy. They bounce back, and that momentum, change in momentum, results in a force pushing against whatever it hits. You assume that kinetic energy is proportional to temperature, and you can show this is actually always true. It's not an assumption just for ideal gases, it's for any liquid, solid. The kinetic energy will be proportional to the temperature. And that the collisions transfer energy to whatever it is in contact with the gas, whatever's in contact with the gas, that force is where the pressure comes from. So if you have these molecular collisions, you can imagine that if you have a larger area, you get the same number of collisions per unit area. And so that's what the assumption is. I'm not going to go through the whole derivation here because it's gone through in the book. But if you work through the different assumptions, you end up getting exactly the PV equals is proportional to the n times temperature with an unknown constant that ends up being, with some more assumptions, you can find out what that constant is and how it relates to Avogadro's number. Okay, so, and we can see how this idea explains just now at a qualitative level, explains the different components of the ideal gas law, the simple gas laws that make up the ideal gas law. So if, by kinetic and molecular theory, if we decrease the volume, but keep everything else the same, the molecules are moving at the same speed, they're going to be hitting the sides more frequently. The pressure goes up. They're moving the same amount. If you make it half the size, then they're going to be on average hitting the sides twice as frequently. The pressure goes up. If you increase T by Charles' law, if you increase T, the molecules go faster, transfer more momentum to the walls, and therefore exert more force. And this, as long as the temperature is proportional to the kinetic energy, then that momentum transfer will go exactly with linearly with T, because it'll go with the square of the velocity. So increase n, the more molecules hit the sides. If you have twice as many molecules, you're getting twice as many collisions. That's pretty straightforward. And change of identity, well, if all that matters is the kinetic energy of the molecule, and the temperature is proportional to the kinetic energy, it doesn't really matter what molecule it is. The molecules have the same kinetic energy. So change identity doesn't change anything. So all the assumptions in kinetic molecular theory motivate what's happening in the ideal gas law. They explain all the different phenomena we see, which is nice. It's a theory that doesn't require a lot of assumptions. It doesn't require any assumptions about the electrons or anything else. It's a simple physical relationship. So, so the one thing that is different between different molecules is the molecular speeds. So first, if you just look at just a single molecule and look at temperature, molecules don't actually have they don't have a single speed. They have a distribution of speeds. And when you take if you take a thermodynamics class or physical chemistry class, you might drive this at some point. It's known as the Maxwell-Boltzmann distribution, and you can see that they have a relatively wide distribution, with a pretty well-defined average. And so when we look at the temperature, the individual molecules have this distribution of velocity, but the average is going to be, the molecules is well-defined. And so as you go to higher temperatures, then you get a distribution that is higher and has a larger average. So that's for, within a single gas, that's what you get. But for at the same temperature, for different masses, you get very different distributions as well. If you have a heavy molecule, so here, let's look at helium, which is quite light, it has very high speeds because kinetic energy is 1/2 mv squared. And so therefore, if if the temperature is proportional to the kinetic energy, for a given amount of kinetic energy, if you have a light mass, you have to have a high velocity in order to have that amount of kinetic energy. You have something like xenon, which is much heavier, then for the same amount of kinetic energy, because it's carrying a lot more mass around, it moves much slower. So all of these probability distributions are actually consistent with the same temperature because of the difference in the masses. And you can work out exactly what the formula is. I'm not going to prove the formula, but let's plug it in to just make sure all the units work out right. So the root mean square velocity. So here the average is defined by taking all the velocities of all the particles, squaring them, averaging them, and then taking the square root. So this would be, let's take an example. Let's take, say, water vapor. So we have square root of 3, and we have, now actually let's pause. What gas constant unit should we use? So we want to get things out that are in terms of speed. So we want a unit of energy that is more like speed. So we know that a joule is a kilogram times a meter squared per second squared. So that sounds like it's a lot closer. So let's go with that. So we're going to do the gas constant in joules. So the gas constant is 8.314 joules per mole Kelvin. Need a little more space. Times the temperature. Let's just say we haven't specified one. Let's say it's at 300 Kelvin around room temperature. And then we divide by the mass, and it's important, if we want this to cancel, we know that a joule is defined as a kilogram per meters squared, second squared, so we want to use the mass in, we use the mass in kilograms per mole, not grams per mole. So this would be 0.01802 kilograms per mole. And so kelvins cancel, moles cancel, and what we get is 6.44, no, sorry, not 6 point, let's, and we get 644 joules per kilogram. But what is a joule per kilogram? Actually, sorry, I jumped the gun on that. We get 644. That's already has the square root taken. The square root of joules per kilogram. Now that looks a little scary until we remember that square root of a unit, that's going to be a problem. Until we remember that, let's move this out of the way. A joule is a kilogram meter squared second squared divided by kilograms. So that just gets the square root of square root of meter squared second squared, which is meters per second. So we get a result that is indeed in the right units. We get that it is 640, the root mean square velocity is 644 meters per second, which is fast. You know, that's, in a second, it's gone 2/3 of a kilometer. So halfway across campus, you know, in a second. So that's very fast. Gas molecules are moving very fast, which is why such small atoms can actually contribute to a large atmospheric pressure, because even though they're really small, there's a lot of them and they're moving really fast.